that. The recording's on. The two items that we're dealing with today deal with places where you would use derivatives. Okay, so the related rates problems are first, and those are going to take some time to get through. And if you have questions, please ask, because I don't want to let you go today without having a firm grip on related rates. Okay, related rates. Have you ever wondered how fast the area of a ripple of a pond is increasing based on how fast the ripple is? What about how fast a volcano's volume is increasing? This lesson on related rates will saturate your curiosity and then some. Solving related rate problems using calculus. The first thing we have to be able to do is we have to be able to take the derivative with respect to time. And that is one of the hardest things. Well, it's not that hard. You just have to realize that when you're taking the derivative with respect to time, you always have to put that in for all of the variables. Okay? The idea behind these problems is very simple. In a typical problem, you'll be given an equation relating two or more variables. These variables will change with respect to time, and you'll use derivatives to determine how the rates of change are related, hence the name related rates. The first and most important thing you are able to do is to find the derivatives with respect to time. So here's some examples that you have to be able to do. Now, I'm going to do the second two first because they're easier than the first one. Not sure why I put a harder one up there to begin with. But when you take the derivative like normal. The only problem is when you're done with it, you put dw dt, dw or dp dt, whatever it is. So for example, if I was going to take the derivative of p, this would be, because again, you bring the 1 down, then there's nothing left there. So the derivative of p would just be dp dt. So this is really perimeter, right? Because perimeter is equal to 2 length plus 2w. So the derivative of this formula would be dp dt is equal to, and then the derivative of 2l would just be 2 dl dt plus, and then the derivative of 2w would just be 2 dw dt. Now, if I had something like 2w squared, you bring the 2 down, so this would be 4w dw dt. You just tack on the derivative with respect to time on all of these. So for example, if I had a squared plus b squared equals c squared, this would be 2a dA dt plus 2b dB dt is equal to 2c dC dt. This one is used a lot. Now this one, the reason why this one was hard is because you have to use the product rule. You have to say u is equal to L, u prime is equal to dL dt, v is equal to w, v prime is equal to dw dt. So the derivative of area, because this would be a rectangle, right? Area is equal to length times width, would be dA dt is equal to, inside, so what is that, dl? Oh, I'm not going to have enough room to write this. dl dt times w plus, and then the outside. So the rules for taking derivatives, they don't change. I mean, we're always taking derivatives the same way. It's just now, every time you take a derivative, you have to put dw dt or dl dt or dA dt behind it. Okay? Does that make sense? All right. So I'm going to give you one, and I'm going to ask you to take the derivative of it. Okay? So let's say, let's just do a formula, because all of them are going to be formulas. Everything is going to be a formula tonight. So area is equal to, let's say, pi r squared. That's not a very good square. No, let's do volume. Sorry, volume is equal to pi r squared times height divided by 3. All right, so that's a volume of a cone, right? Area of the base times height divided by 3. So that's the area of a, and you could use that as area of a pyramid or cone. Doesn't make any difference. Same formula. Oh, this is a, Never mind. I won't do this one because this one's pretty tough. let's just do volume is equal to pi r squared. We'll just do that one. That would be area. That would be area. So let's go area. So area is equal to pi r squared. Okay. So what would the derivative of that be? If you had to take the derivative of that. Two pi r dr dt. Absolutely correct. Yep. Okay. So now let's see what type of problem we're gonna start off easy. I suppose this isn't the easiest one we could start off with. It says a 26-foot ladder leans against a building so that its foot moves away from the building. Okay. Now, I am a very visual learner. So the first thing I do on these types of problems is I always draw a picture. So here's my ladder leaning against the building. It tells me that it's a 26-foot ladder, so I'm going to put 26 right here. Okay. And then it says, and I'll make the ground green. Okay. Then it tells me, so let's change this so it's not so big. Then it says, so that it's against the building so that its foot moves away from the building at a rate of 3 feet per second. So this ladder is moving this direction at 3 feet per second. So now I'm going to label these. I'm going to label this A and this B. So what did they just give me? Well, they just gave me dB dt. And that is equal to 3 because it says it is moving away from the building at a rate of 3 feet per second. Okay, so I know the rate at which that is moving away from the building. When the foot of the ladder is 10 feet from the building, so now they just gave me B. They told me that B is equal to 10. The top is moving down at the rate of r feet per second. So they want to know, how fast is this ladder going this way? So what am I looking for? I'm looking for dA dt. So I got a lot of stuff in here. What formula do you think we're going to use here? It's a triangle. It's a big hint. What formula we're going to use? Pythagorean theorem. Correct. Okay. So we know that a squared plus b squared is equal to c squared. Is any one of these numbers a constant? Is anything a constant, not changing at all? A is definitely not a constant because A is changing. As this ladder moves down, A keeps changing. I disagree with you. The ladder is 26 feet. It's never changing its length. It's always going to be 26 feet. I don't care how far it goes down, that ladder is always going to be 26 feet. Now, the reason that is nice is because if you ever have a constant in your problem, it's just going to cross off. You don't even have to deal with it. So this c squared here, I can get rid of. I'm going to leave it in there just for the time being. Okay, so now we are looking for dA dt. We're looking for how fast this ladder is moving down. So this is my question mark. I have to know everything else. What's A? What is A? They didn't tell me what A is, but I sure can figure it out because I do know the Pythagorean theorem. Yep, I know that A squared plus B squared is equal to C squared. Now, I don't know what A is, so I'm just going to leave that. I do know what B is. B is 10 is equal to 26 squared. What is A? I hope you have a calculator because I'm sitting outside. I don't have my calculator with me. What is A going to equal? All right, so you figure out what A is. And usually they come out nice. I mean, it's going to be either 14 or 15 or 16, something like that. 24, okay? A whole lot more than I thought. All right, so this is 24. All right, now I'm going to take the derivative here. And then I'm going to plug in all my values. A squared, well, that's 2a dA dt plus 2b dB dt is equal to 0. This is a constant. Take a derivative of a constant, it's 0. All right, so now I know what a is. It's 24, so I'm going to plug that in. So that's 2 times 24 times dA dt. I don't know that. That's what I'm looking for. This is what I'm looking for. Plus 2b, well, b is 10, and dB dt is 3, is equal to 0. Well, 2 times 10 times 3, that's going to be 60. 2 times 24 is 48. dA dt is equal to 0. So I'm going to subtract 60 off. So I'm left with 48 dA dt is equal to negative 60. Divide through by 48. So the rate at which that ladder is falling at that given instant, when the base of the ladder is 10 feet away from the wall, is going to be, what is that? If I divide that out, I get 30 over 24, 15 over 12. Take a 3 out of there, 5 over 4, 5 fourths, negative 5 fourths. Now, they don't have a negative up here, but the rate at which that ladder is coming down is 5/4 feet per second. All right, does that make sense? And every problem is a little different. I mean, they're all going to use a formula. They're all, everything is going to use a formula like this. You just have to set the problem up. All right. This one, it's a little bit tricky. It says the radius of a circle is increasing at a constant rate of 0.2 meters per second. Okay. So I'm going to draw my circle in here. What did they just give me? Okay. That's one of those things that you have to look at and you have to try to figure out. They're always giving you something. Okay. So the radius of a circle is increasing at a constant rate of 0.2 meters per second. So what did they just give me? Okay, but what? Okay. They just gave me dr dt. That's because they gave me the rate at which the radius is increasing. It says the radius of the circle is increasing at a rate of 0.2. So I know dr dt is 0.2. What is the rate of increase in the area of the circle? Okay, so I'm looking for the rate of increase in the area. So what am I looking for? I'm looking for dA dt. That's what I'm looking for. I want to know how fast the area of the circle is increasing. Okay, so area of a circle is pi, or area is equal to pi r squared, correct? So that is that's what I'm going to take a derivative of. But then they gave us a little twist at the end. It says when the circumference of the circle is 20 pi meters. Okay, so if I took the derivative of this thing, I end up with dA dt is equal to 2 pi r dr dt. Okay, well, I know dr dt. I don't know what r is, and this is what I'm looking for. So the only thing I need still is this r value, and that's why they gave me this goofy little thing at the end. It says, how fast is the area increasing when the circumference of the circle is 20 pi? Well, circumference is equal to 2 pi r, isn't it? That's circumference of a circle. So then what I did is I said, okay, when the circumference of the circle is 20 pi, so I just did 20 pi here is equal to 2 pi r, divide through by 2 pi. So R is equal to 10. Yeah, so I needed to do that little twist there is how they set these types of problems up. It's like, can these students think through the type of problem? Okay, so now I have 10 here. So dAdt is equal to 2 times pi times 10 times 0.2. I put everything in that I needed. So 20 times 0.2, 20 times 0.2, is that 4? Or is that 0.4? 20 times 0.2, ooh, that's 4. Move it over 1, so that's 4. So 4 pi dAdt. So the rate, the area is increasing, is at 4 pi, and I don't know if this was meter, yeah, meters squared. So that is a unit rate problem. I mean, and there's no way you can teach every type of problem in units rates. It's just impossible. But it's just, they're basically the same thing, just a little bit different on each one. This one, I'm going to let you work through this one. This one is very much like the ladder problem, except a little twist on it. Okay, so I'm going to let you work on it for a little bit, and then we'll come back and see how you do. Okay, give it a shot. All right. Now, did you set up a diagram? All right. So the diagram on this one, it says a railroad track and a road cross at right angles, and an observer stands on the road 70 meters south. Okay, now, usually my drawings aren't the best, but here's my railroad track. Guy standing 70 meters south. Okay, so that's 70. To me, that looks like it's going to be a constant because he's not moving at all. Of the crossing and watches an eastbound train traveling 60 meters per second. Okay, so I'm going to call this T here for train. So they just gave me DD, D, DT, DT, derivative of train with respect to time. All right, we got two T's there, but that's okay. All right, and that is equal to 70 meters per second. All right. And this guy, so he watches this train. It crosses right here. It's going this direction at 70 miles per hour. Okay. Oh no. Oh no. That's 60 miles an hour. He's 70 meters. Okay. So 60 meters per second. At how many meters per second is the train moving away from the observer 4 seconds after it passes the intersection? Okay. So this is the intersection. So what is T here? Well, this is where it's like, okay, it crosses this intersection. It's going 60 meters per second 4 seconds later. How far did that train travel? Where is that train right now? It's right here. It's at 60 times 4, so this is at 240 meters. This gentleman is watching this train. It was there, it was here, then it was here, then it was here, but 4 seconds later, it is here. And we want to know how fast is it moving away from this guy. So let's call this A, and let's call this C. Okay. I know dt, which is kind of goofy, is 60. I know t is 240. What is c? And what are we looking for? We're looking for dc dt. We're looking for how fast this is increasing, because it's gonna go way over to here. So we want to know how fast that train is moving away from that gentleman. Okay. So what is c? Because I know everything else. I know dt is 60. I know t is 240. I know a is 70, and he is not moving. So this is a constant. Okay, he's not moving. That's a constant. So what is c in this problem? And there is where a calculator comes in really handy. I'm going to take a guess at like 250, 260. I am counting on it because I don't have a calculator. Now, do you understand where I came up with that 240? Okay. All right. What is c? Hopefully you're using a squared plus b squared. 250? Okay. So this is 250. So again, Pythagorean theorem. A squared plus, I better put t squared in there because I use t, is equal to c squared. This is a constant. It's gone. So that's gone. So now I have t squared is equal to c squared. Well, if I take the derivative here, I get 2t dt dt is equal to 2c dc dt. All right, I'm looking for this. This is how fast it's moving away. I know, so this is 2 times 250 dc dt is equal to 2 times 240 dd dt, and dt dt is 60. That's a mouthful. Okay, so now I'm going to, hopefully you have your calculator and you can multiply this out. What is 2 times 240 times 60? I know what this is. This is over here is 500 dc dt, 28,800. And then I'm going to divide by 500 because I want to get dc dt by itself. So what is 28,800 divided by 500? 57.6. So that is how fast that train is moving away from the observer. Okay, any questions on that? Tonight's assignment, I will tell you there's a problem almost identical to this one, except it is a cat and a balloon. So what they do is they say, okay, this cat starts way out here at, let's say, 700, and I don't know what the things are. And then there's a balloon here. And they're going to let go this balloon, and this cat starts running toward the balloon, and they'll tell you that the cat is running at, let's say, 3 feet per second. And then they're going to say the balloon is going up at 2 feet per second. And then they're going to say after 40 seconds, how fast is the cat and the balloon going apart or getting closer? Well, that's almost identical to this problem. So you're going to have to take the 3 feet per second that the cat's running and times that by 40. So 3 times 40 is 120. Subtract it from the 700, and that's going to give you 508. So this is going to be 5. So now the cat is 580 feet away. And then the same thing with the balloon. The balloon's going up 2 feet per second, but it's going at 40. It's going to be traveling up at 4 for 40 seconds. So this is going to be 80 feet here. And then this is what you're looking for. You're looking for dx dt, how fast the balloon and the cat are getting closer and closer or farther and farther apart. That problem, that was on an AP exam back of maybe 10 years ago, and I thought it was just the most amazing problem because it's very similar to the railroad track crossing, but there is no constants in this problem because the cat's moving toward, the balloon is going up, the distance in between are changing, so everything's changing in this problem. But the part that was similar was because the train crosses the section and it gives you after so many seconds, so you have to figure out where each thing is at that particular time. So it's a good problem. I like this one. All right. Here is the hardest type of problem that they can give you. Okay? And I'll tell you why. The reason it's the hardest type of problem is because it had the formula has 2 variables in it. And every problem that they give you that has 2 variables, you must do one thing. You must rewrite it with 1 variable. Okay? And I'll show you what I mean. It says assume sand allowed to pour onto a level surface will form a pile in the shape of a cone. Okay, so this sand is dropping down. It's going to form a pile of sand like this that forms something like that, with height equal to diameter of the base. Okay, so we know the height is equal to 2r, correct? Because diameter is the same thing as radius, 2 times radius, correct? So the height is equal to 2 times the radius at all times. Okay, it's very, very important because now I can rewrite, and then I continue on. If the sand is poured at 2 cubic meters per second. Okay, so what did they just give me? Okay, and usually they do give you the formula. So volume is equal to pi r squared h over 3. So what is 2 cubic meters per second? What did they just give us? The rate of what? Okay, I agree, it's a rate. It is a rate, but it's a rate of what? And when you think about it, nope, it's not telling us how fast the height is moving. It's volume. The sand is poured at 2 cubic meters per second. Right there, that should tell us right away, cubic is volume. So they just gave me dV/dt. That's what they gave me, 2 meters per second, cubic meters. How fast is the height of the pile increasing? So what am I looking for? What am I looking for? How fast is the height? Okay, so that would be, I would say that's dH/dt. And that's my question mark. When the base is 8 meters in diameter, so when the base is 8 meters in diameter, so what would the radius be then? Radius would equal 4, wouldn't it? All right, now, this is where it gets a little tricky, because if the radius is 4, I should know what the height is, right? Well, I suppose I could do this in a little different, because that means that h is that too. But since I'm looking for dH/dt, I am going to rewrite this equation with just H's. I don't want any R's in there. I know H is equal to 2R, right? So I also know, a little bit of math here, H over 2 is equal to R. Do you agree with that? Do you agree with this? H squared over 4 is equal to R squared. And why did I do that? Because in place of R squared in this formula, I want to put this. So now I'm going to end up with volume is equal to pi H to the third over 12. All I did is I put H squared over 4 here, and that gave me H to the third, and then 4 times 3 is 12. There's my formula. Okay, so now I'm going to take my derivative, and that is where anytime you have a volume problem like this, you have to get it as one variable. If you don't, you're going to be really going crazy trying to take a derivative. So now it's pretty easy. I've got dv dt is equal to, bring the 3 down, 3 pi h squared dh dt over 12. I'm going to simplify. I'm going to make this a 4. So far, so good. I'm looking for dh dt, so I don't know this. I do know this, dv dt, that's 2, is equal to pi h squared. Well, they tell me the pile is increasing. They want to know how fast is the height changing while the pile increases when the base is 8 meters in diameter. Well, we know height and base are the same, right? They told us that way up at the top. The height is equal to the diameter of the base. So this would be 8 in here, 8 squared, dh dt, that's what I'm looking for, over 12. Oh, I simplified it down, over 4 now. So now it's just math. This is going to be 64. If I cross that out, isn't that 16? So I end up with 2 is equal to 16 pi dh dt. Divide through by 16 pi. And you can just leave your answers like this. This would be fine. I'd probably rewrite it as 1 over 8 pi is equal to dh dt. But that's it. That is the hardest type of problem they can give you, because you have to make sure that you change the variable so it's one variable, and it'll always be, every one of the things are going to be proportional. So it'll say the height is 2 times the radius or something like that. They always will. But that is one of the hardest types of problems that they can give you using a related rate question. All right, any questions on that? All right. I think that was the last of the related rates. The rest of it deals with motion. And I love this stuff. I think this is some of the easier stuff. Most of the times when they give you a function in this class, it's going to be called a position function. They're going to say, oh, this particle is at this position, da, 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 da. So it's usually called a position function. Now, when you take the derivative of the position function, you get velocity. So the derivative of position is velocity. And the derivative of velocity is acceleration. So these are, when you understand this, the derivative of position is velocity, the derivative of velocity is acceleration, you got it made. Now, the absolute value of velocity is called speed. The speed has to be positive. And you probably learned that in physics or something like that. All right, so what is the difference between, let me get rid of this. What is the difference between displacement and distance. Okay, what is the difference? Is there a difference between displacement and distance, or is it basically the same thing? You learned it. Did you remember it? There's the question of the day. And I will give you an example. I'm going to give you this example. I'm going to give you position. Okay. All right. So let me give you an example and let's see if you can. Okay. I am starting right here. Okay. I'm starting at 0. I walk 2 miles in this direction. Okay. Then I turn around and I come back 1 mile. And I stop. What is my displacement? What is my distance? Displacement is 1 mile, correct? And distance is 3 miles. Okay. Got to know that because the next formulas are going to make sure, or you have to know the difference. Okay, so these are two very, very important things in here. It says, suppose that an object is moving along the coordinate line, and that's what it always is. They always say that it's moving along a coordinate line. So here's my coordinate line. The particle is going to move in this direction, then it might move back in this direction, then it might turn around and move back in this direction. So it's always moving horizontally. Sometimes it moves vertically, but this is the type of problem that they're dealing with. We're going to try to find total distance and displacement and all that kind of stuff. So the displacement of the object over the time interval is just basically what you said. It is just from where you start to where you end. So if I gave you a position function, so if I said position at time t is equal to 2t plus 5, and I said, what is the displacement between time 0 and 5? Well, you would plug 0 in here. So your p of 0, and this one's not turning around, so it's kind of a weird one. So time 0, it's at 5, and at time 5, it's at 15, so the displacement would be 10 because it's 10 apart. And it's not turning around. I know it's not turning around because it's a linear function. It's just going straight. Now, the average velocity, this is super, super important because we're going to be talking about instantaneous velocity on the next slide. But the average velocity is displacement over time. That is average velocity, displacement over time. Okay? These are good things to write down. So now, instantaneous velocity is different than average velocity. Instantaneous velocity is the derivative of the position function. That's all it is. And that gives you instantaneous velocity. Now, if you were in physics this year, guess what? It would make things so much easier. Because remember in physics, you always dealt with the height of an object at any given time is negative 16t squared plus the initial velocity. Let's say the initial velocity was 16 feet per second plus the initial height. Well, now if you want to know the velocity, this is a position function. This tells you exactly where that ball is going to go. It's going to go up, it's going to come down. That's the position. This is called a position function. Now, if you wanted to know the velocity of that ball, all you have to do is take the derivative of this. So you'd have negative 32t plus 16. This gives you the instantaneous velocity of this object. That is so cool. I mean, when you start realizing that physics and calculus go hand in hand, if they would teach you this in physics, it would make things so much easier. The speed is the absolute value of velocity. So here is a problem. It says a projectile is shot upward from the surface of the Earth and reaches a height, S, equals negative 4.9, now they're dealing with meters, negative 4.9 t squared plus 120 t meters after t seconds. Find the velocity after 5 seconds. Well, they're telling us that this is a position function. This is a position function. P of S is equal to negative 4.9 t squared plus 120 t. Now they want to know what the velocity is after 5 seconds. Well, if I take the derivative of position, I get velocity. So that would be negative 9.8 t plus 120. Plug 5 in here. Again, I don't have a calculator. If I plug 5 in here and add 120, I get the velocity at 5 seconds. That would give me the velocity of that projectile at 5 seconds. And that's why, 71 feet per second, it doesn't seem, maybe it does, because that's about 10, 50. Yeah, that seems about right, because that would be like negative 50. Okay, I'll buy that. So at 5 seconds, that projectile has a velocity of 71 meters per second. And using correct units is big in this unit. Okay, you got to use those correct units. All right. Acceleration is the derivative of velocity. So if you find velocity, take another derivative, that is acceleration. And then the derivative of acceleration is called jerk. It's a weird name, but it is true. If you ever sit in a car holding a cup of coffee and you just put your foot on the gas pedal, that jerking motion, that is the third derivative. That is called jerk. And that's kind of weird, but usually you never run into a question dealing with the third derivative. It's always position, acceleration, velocity. Okay. Here's where this is all going. This one problem. This is off an AP exam. I think it's a wonderful problem. It says a particle moves along a line so that its position at any time t is greater than 0 is given by the function s of t is equal to t squared minus 3t plus 2, where s is measured in feet and t is measured in seconds. Find the displacement after 5 seconds. Find the average velocity after 5 seconds. Find the instantaneous velocity when t is equal to 4. Find the acceleration. At what value of t does the particle change direction? Where is the particle when s is at a minimum? I am going to let you work for maybe 3-4 minutes. I want to see how far you can get on this problem, okay? So give it your best shot. I know we just went over a bunch of this, displacement, average velocity, and all that, but give it a shot and see what you come up with. All right, let's give it a shot. What did you get for part A? Oh, you already have a bunch of answers. Okay, so let's work this out. I usually, when I do these types of problems, I always put P of t, standing for position. Then I'll put velocity, and I'll find most of them right off the bat because it helps me. So position function is t squared minus 3t plus 2. Velocity function is 2t minus 3. Acceleration is going to be 2 no matter where it is, right? That's acceleration doesn't change in this problem. Find the displacement during the first 5 seconds. Okay, so that's p of 0 and p of 5. So p of 0 is just 2. P of 5 is 25 minus 15 plus 2, so that's 10, so that's 12. So my position, or my displacement, should be 10. I started at 2, I went to 12. Displacement is the difference between where you start and where you stop. So part A, do you understand why it's 10 and not 12? Yes, displacement is the difference between where you start and where you stop. Average velocity. Now, you're not going to get average velocity correct if you didn't get displacement correct, because average velocity is displacement over time. Well, my displacement was 10, my time is 5, so my answer should be 2 feet per second for average velocity. You are 0 for 2. Part C. Find the instantaneous velocity when t is equal to 4. Instantaneous velocity? Oh no, how did you get that one wrong? Instantaneous velocity, I just plug 4 in. 2 times 4 is 8 minus 3, 5 feet per second. And I think that's second squared if I'm not mistaken for velocity. Okay, so 5 feet per second. 0 for 3. Oh man, we better get one of these right. Find the acceleration of the particle. Woo, you got that one right. Acceleration is 2 feet per second squared. Awesome. At what value of t does a particle change directions? When the velocity is equal to 0, the particle is changing directions. Okay, so my velocity function is 2t minus 3. If I set that equal to 0, I will find out when it's changing directions. So I add, so that's 2t is equal to 3. And we didn't talk about this yet. So t is equal to 3/2 or 1.5. So this particle changes directions at 3/2 seconds. Where is the particle when s is at its minimum? Okay, so now this is where it gets interesting. This is where I create a line segment. At time 0, I start at 2. Okay, now after 1 second, where is this particle? Is this particle moving to the right or to the left to start? Because I know at 3/2 seconds, it's at 0. So could you take your calculator and could you put 1.5 into our position function? So 1.5 squared minus 3 times 1.5 plus 2. What do we get? Where is that function? Where is that particle at 1.5 seconds? At negative 0.25. So this particle started at 2. It went this direction until it hit negative 0.25. Okay, so this is at 2. This is at negative 2.5. Then this particle changes direction and it goes this direction for the rest of its life. How do I know it's going to the right and it never changes again? Because the velocity is never 0 again. So this function, this particle, went to the left to start, and then it changed directions and it went to the right. So it says, where is the particle when s is at its minimum? Negative 0.25. That's as far to the left as that particle is ever going to go. And then it's going to go to the right. It's going to keep going and going and going. So whatever values we put in, you could find. Now, I could ask, this would be my next question. My next question would be, what is the distance? How far did this particle travel? How far did particle travel in 5 seconds? So how far did this particle travel in the first 5 seconds? And it's not an easy question. Most kids would not get this right. All of the information is up there, but most students would not get this right. 10.25, not a chance. And the reason is distance. Distance is how far you've traveled. Well, P of 5 is equal to 12. So it starts here, it goes back this way. How far did it travel this way? 2.25, isn't it? 2.25. Then it turns around and it goes all the way until it hits 12. Well, how far did it just travel? From negative 0.25 to 12, it just moved 12.25 units, right? Because I got 0.25 to get to 0 and then another 12. So what is the total distance? Well, 2.25 plus 12.25. That gives me what, 14.5? This particle traveled 14.5 feet in the first 5 seconds. Okay, take a look at it. Do you understand it? Why it's 14.5? Okay. Now, when we get to second semester, then this is the easiest problem in the world, because this is called an antiderivative, and it's the area underneath the curve gives you total distance traveled. All we have to do is find the area underneath that curve, and it will tell us exactly how far the particle traveled. So right now, the only way we can do it is by where did it start, where did it turn around, and then just add up all those distances. That's the only way we know how to do it right now. Second semester, boom, there's a real simple way of doing it. All right. This is one of the problems that you will always get on an AP exam. They will ask you all those different things. A particle moves along the x-axis so that its position at time t is given by t squared minus 6t plus 5. For what value of t is the velocity of the particle 0? Okay, so this is a position function. Position at any given time is t squared minus 6t plus 5. It wants to know when the velocity of the particle is 0. Well, so now I'm going to get the velocity. So that's 2t minus 6. Velocity is equal to 0. That's when it's changing direction. So I just set it equal to 0. 2t is equal to 6. T is equal to 3. At 3 seconds, this particle is changing directions. Okay, does that make sense? When the velocity is equal to 0, the particle will be changing directions. All right, this one's yours. If the position of an ant traveling along a horizontal path at time t is equal to 0 is 3t squared plus 1, what is the ant's average velocity from t is equal to 1 to t is equal to 6? Average velocity. $21. Okay, now I didn't do the problem yet, but average velocity is displacement over time. So I know that the bottom is going to be 5 seconds. Then T1, that's going to be 4, 6, it's going to be what, 8, that's 30, 36 times 3. So that's 108 plus 1, 109. So it starts there, so that's 105. 21 is correct. Yes, very good. So there's a difference between average velocity and instantaneous velocity, because this is the average velocity between 1 and 6 seconds. Now, if I wanted to know what the instantaneous velocity was, that's at a specific time. So if I said, what is the instantaneous velocity at t is equal to 6, then it would be just 6t, plug in the 6 there, it would be 36 feet per second. So that huge difference between average velocity and instantaneous velocity. And here is the last slide for today. It says a point moves in a straight line so that its distance at time t from a fixed point of the line is 8t minus 3t squared. What is the total distance covered by the point between t is equal to 1 and t is equal to 2? Okay, and I would assume that it's probably changing directions someplace in there. We better do this because we're almost out of time here. So the total distance traveled. So I'm going to look at this. I'm going to say, okay, so P of position at 1, that's going to be 8 minus 3, so that's 5. Position at 2, that's going to be 16 minus, that's 12, so that's 4. Now, most people would just say, oh, it's just 1. However, I bet you it changed directions in there someplace. So let's take the velocity is equal to 8 minus 6t. Subtract off 8 there, so negative 8 is equal to negative 6t. Divide through by negative 6. So this function 4/3. So it changes at 4/3. So the particle is changing direction. So at t is equal to 1, it starts at 5, goes in one direction, then changes and comes back in the other direction. So I know the answer is going to be more than 1. Now, I doubt if it's going to be a lot more than 1, but I don't know what, I don't have a calculator, so I don't know what 8, so the next thing I do is I'd plug 8, yeah, I'd plug 4/3 into my equation to see what the distance is there. Okay, so with the calculator, what did you come up with there? What is 8 times 4/3 minus 3 times 4/3 squared? That's a crazy number. So that would give me P of 4/3. Okay, what is that going to equal? $5.3? Okay, so this is 5.3. So the particle started here at 5. It went this way to 5.3. So it just traveled 0.3. Then it went back this way till it hit 4. So what did it travel? It just traveled 1.3. So the total distance that it traveled is 1.3 plus 0.3, or 1.6. I would go with 5/3 because that would be about basically 1.6 after rounding it off. All right, we went through a lot today. Does that make sense? All right. We'll see you next week. And next week is the last session before Thanksgiving, because next week is a long week. It's the 5 days plus the following 2 days right before Thanksgiving. So next week is our last session before Thanksgiving. All right. Have a great evening. Exactly. Bye.